Hello, ladies and gentlemen of Algebra 2B. Welcome to Unit 10. We have this and Unit 11. Unit 11 is short, and then that is the ball game. That is the end of Algebra 2. So hang in there. You're doing great, and let's see if we can't close this out. So exponential functions. We're going to talk a lot about that this unit. So you need to be able to graph, write, and solve an exponential equation. So let's kind of get into it and take a look here. So Sam's working in biology class with a petri dish of bacteria. He estimates that he has a colony of about 25. The entire population doubles every hour. How much bacteria will he have after 5 hours? So he has 25, then he's got 50, then he's got 100, then he's got 200, then he's got 400. So I'm just taking times 2 each time. So he starts off 25, so at the end of the first hour he's got 50, second hour he's got 100, third hour he's got 200, fourth hour he's got 400, so at the end of the fifth hour he's probably got close to 800 bacteria. So take a look at some of the functions we work with. Linear is probably what you're most comfortable with, quadratic probably after that. These are some of the things we just talked about in the polynomial unit. Rational unit, and the square root unit. So it's going to look a little bit different than that. So it's kind of what the graph's going to look like. So in an exponential function, it looks like this. All right? So you might want to, no, don't do that. So you might want to highlight that somewhere, that is what the standard form of a exponential is going to look like. And then I want you to take a look at this. The function is continuous. The domain is the set of all real numbers. The x-axis is an asymptote. The range is going to be greater than 0 or less than 0. It's going to contain the point 0a, which means it's going to be on, there's going to be a y-intercept. So in the graphs of a exponential and its inverse are going to be reflections across the x-axis. So here would be like y equals 2 to the x. Here would be 1/2 x. Those two would be 2 and 1/2 would be perfect opposites of each other. So let's take a look. We've got 3 times 2 to the x. So when I look, if I substitute those in there, so this would be 3 times 2 to the negative 3. So that would be 3 over 8. Okay, so that would be 3/8. For negative 2, that was going to be 3 times 2 to the negative 2. Remember what negative exponents do. So there's my answer. Remember, negative exponents means it moves to the denominator, so that's what I got to do. So that's going to be 3 over 2. So that's going to be 3. So that's going to be 6. And when I get up to 2, that's going to be 12. So I can start to kind of take a look at what this graph is going to look like. So negative 3, you're going to be at 3/8. Negative 2, you're going to be at 3/4. 3/8 is going to be down here, 3/4. Negative 1, you're going to be at 3/2, so that's 1.5. At 0, you're going to be at 3. 1, you're going to be at 6. 2, you're off the grid. So it's going to look like that. So that's going to be what your answer is going to look like. So domain and range. Domain, all real numbers. Range is going to be, y is always going to be greater than or equal to 0. Right, because this is where I bottom out right here on the bottom. Right here where y equals 0. So if I take a look at this, 2 to the 1/2 of x, this is going to look a little bit different. So when I do that, it's going to look something like this. So when I substitute this in, -3 will actually give me a positive 16. Let me show you why. So it's going to be 2 times 1/2 to the -3. So that's 2 times 1/2. Well, let me back up. 2 times 1/2 to the -3, but negative flips it around. So that's going to be 2 times 2 to the 3rd. So that's going to be 2 to the 4th, which is 16. Similarly, if I put that in for 2 times 1/2 raised to the -2, so that'll be 2 times 2 squared, so that'll give me 8. Then the pattern will keep going. This will be 4, 0 will be 2. Now when I get to 1, that'll just be 2 times 1/2, which should just be 1. And then when I get to 2, I'm at 0.5. So I can start to kind of think about what this is going to look like a little bit on the graph. So at -3, I'm all the way up at 16. I'm off the graph. At -2, I'm at 8. -1, I'm at 4. 0, I'm at 2. 1, I'm at 1. 2, I'm at 0.5. So this starts to give you an idea of what this is going to look like. So domain, again, all real numbers. Range is going to be y greater than or equal to 0, greater than 0, because it's never actually going to get to 0. So it's just going to be y greater than 0. Domain, all real numbers. So growth is going to be if b is greater than 1, and decay is going to be if b is less than 1 but bigger than 0. All right, growth means it's going to swing up like this. Decay means the graph's going to swing down like this. So what will the value of a car do? That's going to decay. Gold fluctuates up and down, but for the most part, it will grow. A house will fluctuate up and down, but for the most part, it will grow. And electronics, computers, they definitely decay. They are never worth nearly as much as when you first buy them. So cars decay. Gold, houses, jewelry, that fluctuates because sometimes it can go up, sometimes it can go down, but electronics definitely do decay. So determine whether each function represents growth or decay. The 1/5 is my giveaway that's going to be decay. The 1.2, that's greater than 1, so that shows me even though it's small growth, it's still going to be growth. So if you buy a car for 15 grand, okay, the value decreases at a rate of 8% per year. Write an exponential function for the value of the car after X years. So I start off 15,000. So it's going to be 1 minus 0.08 times t, where t is your years. So this becomes 15,000 0.92 times 4. So 0.92 raised to the 4th times that is going to be 10,745.89. There is my total dollar amount. So after 4 years owning the car, instead of 15 grand, it's worth 10 grand. Suppose you start an experiment with 45 bacteria that double every hour. So this is kind of similar to that first problem we looked at. Write an exponential. So I start off with 45. 45 is my initial starting amount. And it doubles, so that means it's going to go by 2, where x is my hour. So 45 times 2 raised to the 4th. So 2 raised to the 4th times 45. So after 4 hours, I'm going to be at 720 bacteria. All right, so a radioactive substance decays hourly. Write an exponential function to model the amount of the substance y left x hours after 1 p.m. Okay, so at time 0, I'm at 1250. And at time 3 hours after 1 p.m., I am left at 10. So let's take a look at what I got here. So 1250 equals 1250 times b raised to the 0. That doesn't help me very much. But what I can do is this, 10 equals initial starting amount, 1250 times b raised to the 3rd. So what I can do here is this. I'm going to divide by 1250. And I should get a decimal, so that's going to be 1 divided by 125. So it's going to be 0.008 equals b to the 3rd. So what I do then is I raise it to the 1/3 because that will cancel it out. So if I raise my answer to the 1/3, I'm going to get 0.2 as my answer. So that means that my decay rate is going to be 0.2. So my function is actually going to look like this. All right, the amount I have is going to be 1250 times 0.2 raised to the power of x. So that's what my function is going to look like. But notice all I did. All I did was substitute that into my original equation, y equals abx, substitute in what I knew, and solve for what I could. So in 2000, the population of Phoenix was 1321045, increased to that in 2004. Write an exponential function that could be used to model the population of Phoenix. Write the function in terms of x, the number of years since 2000. So we need to play around with what a growth rate will look like. So let's do this. So in 2000 at time 0, so my initial starting amount is going to be 1321045 times whatever my growth rate is, time t, and that's going to equal something. It's going to equal my total. So when I go to do this, I'm going to use this information right here now to help me out. So I'm going to take 1331291 equals 1321045 times b raised to the 4th. So now all I'm going to do is divide. So I'm going to divide this that goes away. This becomes 1.0077. It keeps going, but I don't really care. So now I'm going to raise that to the 1/4. So I should get something like this. 1.0019. So that's my growth rate right there, something very, 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 very small, 0.0019. So my equation then is going to be, population equals 1321045 times 1.0019 raised to b. In this case, it would be time, so I'd put t. It kind of depends on what the problem's asking. So if it's asking for 2015, that means t is going to equal 15. So if I substitute that in there and multiply it, I'm going to get 1359879.112. So round that to approximately 1359879. So approximately 1,359,879. So just round it. All right, so let's solve these quick. Well, notice how these two have the same base. So that means 2n plus 1 is going to be equal to 4. So that means 2n is going to be equal to 3. So n will be equal to 3 over 2. Over here, this one's a little tougher, but notice something here. 1 over 64, that's like 1 over... That's like 1 over 4 to the third. Well, if I bring that to the top, if I work backwards, I can say that that's like negative 3. So now I can say 2n minus 1 equals negative 3. So 2n is going to equal negative 2. So n will equal negative 1. So this is a little tricky. You got to do a little work with, you got to remember kind of how those things work with exponents. But other than that, I think you can figure it out. All right, play around with that. Let me show you some tricks on your calculator sometime, and we'll talk to you later.